Scattering, elastic laser scattering is actually a really useful technique. This is a study where they looked at, let's see, they combined extinction. This one is actually not scattering. This is looking at extinction and trying to distinguish extinction from the absorption, extract the absorption from the extinction. And I think they measured scattering, because extinction is a combination of absorption and scattering. So when you send a laser beam through a flame, some of the light's going to be scattered, some of the light's going to be absorbed by the particles, and some of the light's going to make it all the way through. So you measure the light that makes it all the way through. So if you're trying to understand, say, like dispersion exponent, you want to figure out how much of that is because of absorption, because for that one, you don't really care about the scattering. You want to know the absorption cross-section. That's the same thing that is true for the optical band gap. So in this experiment, what they did was sort out the distinction between absorption and scattering that were contributing to the extinction. Okay, and they did this at 2 different heights in this flame. And this group, this is Stephen Will's group, and they have very nice setup where they can look at the angular scattering, so they can capture, and then the scattering cross-section will change with angle, right? It's like the differential scattering cross-section will change with angle. So what they can do is like get entire scattering and then identify the absorption itself. So here they have an absorption cross-section as a function of wavelength. Well, actually, that's the extinction, cross-section, a function of wavelength. They extract out the absorption, and they do this at 2 different heights in the flame. And then from either you could turn this into a dispersion exponent, or they turned it into an optical band gap, and I'll talk about this again in a minute. They could get the young soot versus mature soot and map that out. Okay, so it's actually, this is a complicated process. It's a complicated but very nice experiment that they've done. It's really hard to get the particle maturity, as we've talked about, without actually putting a probe into your flame and trying to measure the particles by any perturbed things and stuff. So this is one technique that you can use to do that type of measurement. Remember, earlier I was saying that extinction is really hard to use because you have the scattering effect that can perturb everything. So this is another way of doing it besides using a technique that's only sensitive to absorption like LAI or photoacoustic spectroscopy. Here's another technique where they did multi-angle laser scattering again, and measured extinction, and then sorted out the difference between absorption and extinction and scattering that were contributing to their extinction. And you can see this is another. They used a co-phone diffusion flame, and you can see here they did multiple techniques. They used LAI. Tire LAI is time-resolved LAI. So they did time-resolved LAI using a model, a conductive cooling model, so that they could get the primary particle size. So that's on the left-hand side, a 2D image of what they extracted for primary particle size. The middle is from the scattering, they could get the radius of gyration, so that gives you the radius of gyration of the aggregate itself. And then on the right-hand side, they measured the extinction. So they did all of this as a function of location in the flame. Okay, so then they turned this into all of these different figures are related to trying to back out the dispersion exponent they call alpha in this case, or the angstrom coefficient, whichever term you want to use. So using the wavelength dependence of the extinction and backing out the scattering, they could get so you see on the right-hand side, they have the dispersion exponent is equal to the alpha from extinction minus the alpha from scattering, and that gives you just the absorption. And that allows them to get the dispersion exponent if they do this as a function of laser wavelength. So this gives them a measure of the maturity in the flame at different places in the flame. So, and so all these ones have color codes up to the right side. So it's a really interesting approach and very tedious and hard to do, and has significant error bars because you're making all these measurements that are really kind of hard to make. Okay, so let me then also talk about how you would use laser-induced incandescence to make this kind of measurement of the particle maturity, where LAI is specifically just sensitive to the absorption cross-section, because anything that scatters is not going to heat up the particle, right? So the way we do this is we use different laser wavelengths. This I'm going to show you a case where we use 2 laser wavelengths, just the fundamental 1064 and 532 for the laser. And again, that's the equation of the dispersion exponent is the absorption cross-section is proportional to the lambda to the negative dispersion exponent. Okay, so here we have the peak LAI is a function of fluence, kind of like those curves I was showing you before, and see how they're different for the different wavelengths, different laser wavelengths. So the cross-section goes down as a function of wavelength, where since the dispersion exponent is positive, it's greater, tends to be 1 or greater. The larger the wavelength, the lower the absorption cross-section. So you need a higher laser fluence. You need more photons in order to heat up the particles to the same amount if you have a longer wavelength. So for 1064, you need almost twice the number of photons to heat up the sample as you do at 532. So notice that the fluence is higher for 1064. You can take the absorption cross-section and get the dispersion exponent. You need the cross-section at 532 and 1064. But notice that we know what the wavelength is. All these other parameters on the top are the same, except for the wavelength is different, and you can assume we're trying to get the dispersion exponent. So if you take the ratio of those cross-sections, everything kind of falls out because they all cancel, except for the lambda to the dispersion exponent. So that allows you to get the dispersion exponent. And the way you do that is by taking the ratio of the fluences at which you hit the same, basically the same LAI signal. The same LAI signal, so when a particle gives an LAI signal, it doesn't matter. Remember what LAI signal depends on is the volume of the particle times temperature to the 5th power. So at an LAI signal, the particle doesn't care whether it's been heated up by 532 or 1064. If it's at the same signal, it's at the same temperature, right? So it may take more photons to get there, but when it's there, so you're there, okay? So let's just say it's path independent. It's right? Okay, so at the same LAI signal, so see where the line crosses those two, then you take how much 1064 light did it take to get there versus how much 532. So you take that ratio, and that gives you the ratio of cross-sections at those 2 wavelengths. That then can be used to get your dispersion exponent. It's actually pretty straightforward once you start sitting down to look at it. Okay, so now you have this in your head. You just get these different, how much more light does it take to do 1064 to 532? And we can do this now at different places in the flame, right? And that will give us dispersion exponent at different places in the flame. So this is, all these different heights above the burner. And you see it's all 1064 on the top, all 532 at the bottom. We match where the signals, the peak signals are as a function of fluence. And then boom, that's where our fluence, so we take the ratio of the two fluences at those wavelengths, and it gives us the dispersion exponent as a function of height and of length. Okay, so we go back to this flame. So these data were taken in that flame. There's our dispersion exponent. You saw that the other day. People sometimes talk about the E of M ratio. That's related to the cross-section. So you'll see that nomenclature. You can always look back in your notes and get that where that comes from. Remember, yesterday, I walked you through how we take a dispersion exponent and turn it to carbon to hydrogen ratio, right? So we did that yesterday. So here we are. Now we know the carbon to hydrogen ratio because we know the dispersion exponent. Okay, so what do you think we can get now once we have the carbon to hydrogen ratio? We know the age of the, so what else do we know? What kind of parameters do we know specifically? Density, yes, who said that? Who said density? I heard a couple of people. Density, yes, density and specific heat, right? So we did that yesterday. We were like, okay, yes, exactly. Density and specific heat, right? So now, just by doing the LII fluence curves at two different laser wavelengths, we can get the density and specific heat. And we know temperature, like I'll talk about that in a minute, and we can actually get the whole thing. You could assume a temperature, you could model a temperature. In this case, we measured temperature using cars. Okay, so now we have density and specific heat for the particles as a function of location in the flame. You know, it's not like a fancy plot, and it should have error bars and stuff, but at least it gets us thinking about it and starting to think about how we do this, like how you can actually get all the parameters you really, really want in order to understand your subparticles. Okay, okay, optical band gap. I ran through that really fast because I was worried about our time yesterday. So I just want to go back for a minute. You can do this in situ with a laser. Again, it's nice to have a technique that depends just on absorption cross-section rather than extinction, because extinction can be complicated. But you can do it. So here's an experiment where they kind of ignored the scattering well, you can also calculate what the scattering might be. But as a function of wavelength, if we ignore scattering, you can get an idea of this dispersion exponent. They used it to get optical band gap. To me, it's like the same, optical band gap, dispersion exponent. Dispersion exponent, I actually have an equation that can relate it to everything else, so I like to think of it in terms of dispersion exponent. But just, they're related, and this is how people think of the optical band gap is, and this slide was in your set yesterday. If you have a molecule, so on the left-hand side, you have a molecule, and those blobs are what we call molecular orbitals, so that tells you something about the electron density in the molecule, so the different states in the molecule. So when you have, so remember we were talking about p orbitals. When you have a double bond, those p orbitals share electrons, and you get a pi molecular orbital. So when people talk about pi orbitals, they're talking about double bonds, and the sharing of the electrons between these double bonds. So in a pH where you have all these aromatic structures, you're going to have a lot of sharing of electrons in these pi orbitals. That pi orbital, so that for a ground state pH, the highest occupied molecular orbital, so the highest state that has electrons sitting in it is what you might call the pi orbital. When you excite the molecule with, say, a laser or something, it absorbs a photon and it promotes one of those electrons into another state. And people usually try to understand what the lowest unoccupied, so where could that electron go? It can't go into an orbital that already has electrons in it. So it's going from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. We usually denote that excited state with a star, so that's pi star. So it's going to go the lowest unoccupied molecular orbital for one of these things that has a lot of aromatic structure is it's the pi star orbital. So this is kind of what people are talking about when they talk about the optical band gap. It's right usually in the optical range for absorption, for that promotion to the excited state. Okay, so that optical band gap, if you look at the graph in the middle here, there are 4 different PAHs sitting up there, and they increase with size going to the right. And if you look on the right, that dashed, that's the optical band gap, and that dashed line corresponds to the optical band gap. As you go to larger molecules, the optical band gap decreases. And at the same time, we say the conjugation length increases, and that's just the size of the pH. The optical band gap can also decrease when you stack these PAHs on top of each other. You have interactions between them, and the optical band gap can also decrease when you have stacking. So people sometimes try to equate the optical band gap decrease with stacking structure in these particles. Okay, so that's the optical band gap. The way people measure it is the same way you would measure a dispersion exponent. You get the absorption cross-section as a function of wavelength. And then what they usually do is say, so the equation on the bottom is what they use to calculate the optical band gap. And EG is the band gap, the energy of the gap. And they usually take these curves, they plot the square root of the extinction times the photon energy, plotted as a function of the photon energy, and then take slopes for different parts of the line and extrapolate to the 0 intercept, x-intercept. So that equation, when you rearrange it, you have a slope and an x-intercept, and that will give you the band gap. And notice that sometimes they'll say, okay, we have multiple band gaps. That's not really surprising if you have multiple different types of species running around in your sample. Okay, so just kind of like backing up to, so you can do all of this in situ, either with UV visible spectroscopy. You could probably do it also with, if you're looking only at mature soot, with LAI measurements, as long as you had different laser. If you had a dye laser, right, and we're tuning through the wavelengths with your dye laser, you could probably do that. Okay. Well, let's see. This is photon. You'd need more than a dye laser. You'd actually need, because dyes are, in the kind of longer wavelengths, 500 to 700 would probably be dye. You'd need to double and maybe triple your dye laser to get the whole full range here. Okay, so this is how people can measure this this is a measurement that's made in a flame and mapped out. What their answers are mapped out on this flame. So they have volume fraction measured with LAI, and then they have what they get from the optical band gap. They can also get the conjugation length is on average they say it's 10 rings or about 1 nanometer. So that's really interesting that you can actually do this in a flame. And it would be nice. I haven't seen anyone do this, but it would be nice to compare that with other measurements in the flame. Yeah. Okay. There's spectral emissivity or emission, and you can combine this with extinction. Here's an experiment where they did both and compared them. So the way this works is you don't need anything. You just accept a detector and you look at the soot emission, right? Soot is already hot in the flame. You see it's yellow or orange, has different colors, right? So you look at that emission, and that gives you a lot of information about, if you look at the wavelength dependence, and it can tell you the temperature, and once you know the temperature, then you can get a volume fraction. It's actually quite complicated. So it seems like the simplest techniques to implement are the most complicated to analyze. That's kind of like how it seems like that's true. But you can do it, so people have done it. So the Planck function is on the bottom. That's the function you're going to use to try to understand the emissivity of the particles. Now here's the one of the issues is for a black body, this parameter emissivity is 1. So that's what defines a black body. You have a Planck function, and that parameter is 1. That is not true for a soot particle. So that's where where I was saying, oh, the cross section is 1 over lambda to the dispersion exponent, or when I said that the LII signal is dependent to temperature to the 5th power. If you integrate it over all wavelengths for a black body, the emission that would be T to the 4th power. That's the Stefan Boltzmann, when you integrate over the Planck function, and you have emissivity of 1, that's what you get. But soot is not a black body because it's too small. So if you consider that it's like way smaller than your wavelength of light, then you can use a Rayleigh approximation, and you basically have 1 over lambda type of emissivity. But it isn't exactly lambda to the 1 because, remember, you have that dispersion exponent that isn't always 1. So you have this weirdness related to the maturity of the particle itself. Okay, so that aside, if you make some assumptions about the emissivity, you can back out, using this equation, you can back out a temperature because you have a wavelength dependence. If you're looking at recording the emission as a function of wavelength. And once you have that temperature, then you can get the volume fraction. Okay, so this technique requires some information about the optical properties, right? Because soot is going to evolve in your flame, so it's going to have different optical properties depending on how mature it is, right? It's actually kind of nice because you can use it in all these different configurations, so there are a lot of advantages to it. If you kind of want to get a rough estimate, it's actually a pretty nice technique for doing that. And then people use it, like, what's one thing that's nice about it is, a lot of these techniques, you have to average your signal over a certain amount of time. This, you could use do a turbulent, system that's not stable. And oh, no.
Maybe just the last 60 seconds or so. I'm not sure where they died.
Excellent, it still works. Excellent.
Sorry about that.
Thank you.
Just give me 1 second to get back up
Okay.
there.
All right. Okay, I get the thumbs up. Okay, so this is a nice technique for doing for some configurations. Okay. Okay, so let's move on. So this is a technique that I talked a little bit about yesterday. Remember, we were talking about X-ray techniques, where implementation of X-ray techniques, where you actually basically take a core electron from the core atom and promote it somewhere. In this case, you're promoting it up to some balanced state of your molecule. And so you're going from a core to your pi star. Remember your LUMO, your lowest unoccupied molecular orbital, your pi star. And then you remember you have the cascading of electrons, and you can measure this in different ways. And then, so remember the pi star is associated with like the aromatic type molecules. The sigma star is associated with the single bonded type chains, molecules, carbon bonds. And then we can look at CO oxygenated species. So this is a kind of a useful technique. This was extracted from a flame, and you do this technique under vacuum. So notice I say in situ up at the top. This is a technique, this is in the soft X-ray range, so we're at the at 285, 284 EV, so your photon energy. A soft X-ray beam is not going to make it through your flame, or at atmospheric pressure. Like if you can do low pressure type measurements, but at atmospheric and higher pressure, you're going to have problems. Now there's a beauty to hard X-ray measurements in that they can go through a high pressure system. So you can get a hard X-ray beam through, so that's like up to like higher than 200, it's like more like 2,000, let's say 10 kilo EV. So I don't know where the cutoff, like maybe it's around 10 keV or 10,000 EV is a hard X-ray, and that can make it through whatever system you have. The problem is it's hard to do spectroscopy at those photon energies, right? You're not accessing these transitions. So, so here's an energy level diagram. So you have your carbon, the electron you're pulling off is your 1s electron, one of the core electrons from your carbon atom. That's going up to your pi star molecular orbital, right? And that's what we call next half, so that's absorption. It is possible to do X-ray Raman. So, and in this case, you could look at the Stokes band, you take your, say, hard X-ray pump, go up to a virtual state, not a real state, and then it comes back down. So it's kind of like a quantum type of effect where you go into a virtual state and come back down to your pi star state with your Stokes photon, okay? So that's X-ray Raman. The difference between those two photons, between the one that you put in and the one you get out, is your transition. It should be the same as NEXAFs. It should be the same as absorption if you do this technique. In this case now, you can send in a hard X-ray as your pump and get out a hard X-ray as your probe. So now you're actually able to make an absorption measurement in a high pressure system. Okay, so we decided we would try this experiment with a flame. This actually took a year to convince the synchrotron that it was okay, because the way you do this technique is you have the X-ray. So in this figure, the X-ray beam is coming from the left. The flame is right in the middle there, that orange thing. The detector is right underneath the flame. And this is why we built that little Henkin burner, is for this experiment, because if you want to be, the detector is right, it sits solidly right underneath the flame, and if you want to go to the top of the flame, you have to have a tiny flame to move it up and down. You don't have a lot of space. The scattered light for this, the light that's emitted, hits that big bank of silicon mirrors. It's like huge bank of mirrors. They're just silicon wafers. It hits that big bank of wafers and comes back and is focused down onto that detector. Okay, so you don't want to have air in the way. So what you do is, let's see if I have this in a photo. Yes, you put a big bag between your sample and the mirrors. So and that bag is full of helium, which doesn't absorb your light. So it's a nice gas to have, but you have to have it in a big bag. So you can imagine, so not long before we proposed this experiment, there was a French group at Soleil was trying to do an experiment with a flame and had a helium bag and set the bag on fire, and then the hutch went on fire, and it shut down the whole synchrotron, and like it was a disaster. So we were like, no, we can do this, we can do this, we can do this. So we put a plexiglass box around our flame, so there's no way that the bag would hit the burner and make a disaster. So that's what it looks like when you're running the experiment. And then you're sitting over in another room trying to watch on a camera to make sure your flame is okay. So here's the ex situ measurements, absorption measurements, and here's the X-ray Raman measurements. So it was really hard to do these measurements. And then in the end, what I didn't account for was the fact that we actually have CO and CO2 in the flame, right? And technique is going to be sensitive to the gas phase too. So we're actually, what we end up seeing is, so CO and CO2 have nice, strong features, and we see mostly a very large feature right where we want to see other oxygenated species in our particles. Okay, that aside, that's fine. What we did see is this interesting pi star peak. And it did something we did not expect it to do. So what we're expecting was, like you've been sitting here thinking about soot for the past almost 3 days, right? And you know that as you go up in the burner for one of these burners, the soot gets more mature, right? Yeah, so you're gonna have more aromatic, you should have more pi stars you go up in the flame, right? That's not what we saw. What we saw is it was high, low in the flame, and then it goes down. And then it has kind of a little shoulder there, and then it goes down, and we actually don't know what these results mean, so we have not published them because we're still trying to figure out what's going on. That's why that's why I was showing all these other measurements for this particular burner, not because it's like an interesting burner, is because we did this experiment, we can't figure out what's going on. And we did it multiple times, and we kept getting the same result. Then we put I won't show you all the results, but we did a premix burner, we did a slop burner, we did a whole bunch of different burners, like we're trying to sort out what's going on. So this is kind of like a little bit of annoyance, like, because I can't figure it out. So we'll see, hopefully we figure it out. Okay. Okay, particle coating. So if you're doing experiments, you're gonna probably come under conditions where the particles are not gonna be homogeneous particles. Like you might be doing, say, engine experiments and they get coated with oil, or you're in a tailpipe and you're starting to get coated with other species that are emitted along with your engine, right? Along with your subparticles from your engine. Or you're in the atmosphere or whatever. So there are a lot of different cases where you're gonna have coated particles. So I just wanted to show you some results that are kind of something to keep in mind when you're doing these experiments, and maybe ways that you could use the techniques and develop the techniques to be able to measure coatings. I won't give you all the answers because we haven't, people haven't sorted them all out. But it's really important to understand coatings can have an impact on the optical properties of the particle. People are fascinated with them because of climate change. Like coatings could, there's results that indicate that coatings enhance particle absorption. So if you have a particle in the atmosphere, it gets coated, it can enhance the absorption, possibly. But the field measurements don't match the lab measurements, so there's a lot of controversy in atmospheric science. So it's worthwhile thinking about this problem. Okay, so let me just show you some of the results we have for coated particles. So here's something you can do if you want to study coated particles. We have a flame. There are probably better ways of doing this, extracting from the flame, but we just send a flow of air or nitrogen across the flame. We sent our particles through, a size selector, DMA, and selected one size, sent them through the particle coater. So we have just like a tube with some, we were using oleic acid because it's olive oil, and it was at Sandia, so we had a lot of safety rules, and it's a lot easier to use something that's not toxic. And it's a good coating, actually. It's like kind of right in the range of what you might expect for coatings for diesel particles. So we just heat up the coating, send that through, and then the thing on the top of the particle coating chamber is called a denuder. A denuder is just basically a hot tube that takes off coatings. So it's basically a little furnace, and it vaporizes the coating. And then we can send that. We can intersect it with the laser. We can send it through another scanning mobility particle sizer and get the size distribution from it. We have, again, the CPMA for particle mass. We talked about that yesterday. And we can do a lot of other analysis. Okay, so we have this experiment. So here's, particle. Here's what happens when you coat it. So even if you put a very, very, very light coating of oleic acid on a particle, it restructures. Remember talking about restructuring yesterday? It clumps up into a little ball that changes its properties. It changes, actually a fair amount of the properties. So because it has less surface area for the volume of the particle itself. We can look at that using our technique. Remember I was talking to you yesterday about atmospheric scientists who do a mass mobility. They do a mass measurement and mobility measurement, and they can tell something about how clumped up a particle is. This is how they do it. So here we take a particle, we size select it. Remember it has multiple charges, and then when you send it back through SMPS, you see multiple peaks. The bottom is sending that same particle through the CPMA to get the mass, and you see the particles are different sizes even in the mass. If we slightly coat it, the particle, the size gets smaller, the mass gets bigger, right? Because you're clumping up. You have a little coating on there, but it still looks like it's a smaller particle to the SMPS because the mobility size is different. And then if you coat it some more, it gets heavier, and then it starts to get bigger. Okay, so that's when you put a really heavy coating on it. Okay, then if you send these particles through the denuder, you take off the coatings, right? And then they all come back to the same size after they've been coated and then denuded, but still they're all scrunched up. They're still small in size because you've restructured it, and when you took off the coating, it didn't come back to life. It didn't fluff out again, right? It still stayed restructured. Okay, but the mass actually comes back to the original mass. Okay, so here's what happens now if you do laser heating on that particle. So those are the TM images for it was coated and then laser heated particles. So on the top is what we call a light coating. It's 25% by weight. The middle is 72% by weight on the coating, and the bottom is 94% by weight. The line right in the center is the original peak, uncoated, just original fluffy type particle, right? So you put the light coating on it, and it restructures, it gets small. So the light coating is the blue line. And it gets bigger, remember, the middle one, it gets bigger, and then the heavy one, it gets even bigger. So those are the blue ones. That's just what I was showing you before in the last slide. If you laser heat the particles, so you coat them and then you laser heat them, you start to get a little fragmentation, right? So you start to get, so the top one has a light coating, and you get, it mostly stays the same size, mobility size, but you get some smaller particles. I think you're basically fragmenting a little bit. You actually, so the green dashed lines is just laser heated. So you have them, you've coated them, and then you've laser heated them. So the second one down, you see that it's the same size, and you're getting more of those little sizes. And then the last one down is you don't really see too much of an effect at all. It's like it's smaller, but not a whole, like the size distribution doesn't seem to change all that much, right? So if you then denude, oh, was I looking at the wrong line? Oh yeah, no, it's looking at the right one. So it's the same as the original peak. So you have some of those little fragments coming off, but it's, you're basically not changing the original peak very much. And then the third, when you send it back through the denuder, and you take off that coating, the particles so the first one doesn't change very much. It had a light coating on it. You fragmented some, right? That's the red solid line. You fragmented some. Then you try to take off the coating, and that doesn't change very much, right? You basically blew off a few probably particles or whatever. The second one, you blew off, you blew off particles. So the red one is when you still have the coating on it, but you also generated little oleic acid droplets as well. So you see a lot of oleic acid droplets coming off. You've vaporized, or maybe they recondensed. And then when you denude it, and those all go away, and you come back to that original peak curve, right? And then on the bottom one, this is kind of the fascinating one, is you come back to the kind of the original curve, and it, so you get rid of all the coating, you just come back to the original curve. And this is going to be interesting when you look at the laser heating part. What we think is happening is, once you have some coating on the particles, when you go to laser heat the particle, it gets hot, right? And now you have like this coating that's like intermixed with the particle. And once it gets hot, it vaporizes, it goes into the gas phase. And you know what happens in the volume when you have a phase change, right? You go from a liquid to a gas, you have a huge volume change, right? Boom, and the particle flies apart. So in the top one, I think we don't actually get rid of all of the coating. The particles are still largely coated, right? But we blow off some of the little arms inside the coating. And then when you go to denude it, it comes back to the original size. But when you first laser heat it, you don't really see much of a change in the main peak itself. You just see little arms coming off. I kind of like to think of this type of thing as almost like popcorn. Like you pop the popcorn and it goes poof, and now you have this thing all spread out and little arms coming out and stuff. Okay, so this one, we can notice how we can add onto this PMT, and we can actually do LAI measurements. Okay, so here's LAI with 1064 on an uncoated particle, just like I was showing you before. We coated the particles, and notice that the LAI peak curve now shifts to higher fluences. What do you think that means when the curve, you add a little coating and the curve shifts to higher fluences? And so you've shifted the absorption for the amount you're needing to heat, right? Yeah, you're shifting the amount you need to heat. And that could be the absorption, cross-section might change, or it could be that you're boiling off the coating, right? Another thing you could be doing is some of that heat could be going to boiling the coating, right? Or vaporizing the coating off the particle. And remember, I was showing you, like it looked from the data, like you're actually vaporizing the coating from the SMPS and CPMA data. Okay, so shifts even more, right? Add more coating, now it shifts even more. Add more coating, it shifts even more. And then it stops shifting. Oh, and then it goes backwards. So I think what's happening here is that you're actually not, once you get to high enough coating, you don't have enough laser power to actually boil off the coating, and the particle just starts, it still keeps heating up, but you're not boiling off all the coating. So you actually still have it heating. It goes up to a sublimation point without fully boiling the part of the coating away. And here's what happens if you send it through the denuder first. It is like the original curve, basically. So it's really the coating that's having an effect on how many photons you need. So I'm not going to run through all the math to show you how you calculate the coating, but the fact is you can use then the shift in these curves to tell you how much energy it takes to boil off the coating, right? Then you get information about the coating itself, right? So this tells you something. If you can do this experiment, if you have a stable enough sample, you can do this experiment and tell something about the coating. So then, this is all part of the data analysis. And in the end, I think what happens is this shows you how much coating. So remember, you go up to a certain point and you stop boiling off all the coating. This just shows you what the average amount of coating is and the vaporized mass of coating. And you stop boiling off all of the coating at about 65 or 70% of mass of the coating. So it deviates from that line. So that can tell you something about what your coating is or some of the properties of your coating. Okay, so let's talk about just LAI and the effect of coatings on LAI, right? So say you're trying now to figure out the primary particle diameter using your code, your LAI code, and you're looking at the decay rates. If your particle's coated, that could be perturbing your analysis, right? So now you're like, oh my gosh, I have to worry about whether or not my particles are coated if they're inside an engine cylinder and I'm trying to do this, right? So this is something to keep in mind if you ever are using this technique, or if you see a paper where someone's using this technique. You have to just keep it in mind. So this is the curve that is really noteworthy is this one. Remember, when you coat a particle, it restructures it. So here's your stringy particle, right? It doesn't always restructure. It depends on the coating itself. But so here's your stringy particle. Here's the same size particle restructured and what the LAI decay rate looks like. So by restructuring the particle, your conductive cooling rate is changing significantly, right? It's slowing down because you don't have as much surface area exposed to the gas phase to cool your particle down. So you have to, think when you do the calculations, what does my particle morphology look like? Usually when we do these calculations in LAI, solve the energy and mass balance equations, usually we assume we have a stringy particle and that every single primary particle has contact with the outside air, with the ambient gas phase. But if you're restructured, that's not what's going to happen. So this is something, and I've been trying to figure out how to do this analysis, and I think you need a little bit more data information in order to actually get a reliable analysis. Okay. Okay, coating. So the fact that that happens, once you see something that has an effect, you can either think, oh my gosh, that's a drag, it's going to make it hard for me to figure something out, or you can think, oh my gosh, that has an effect, I could use that, right? So it's possible that you could use that information to tell you something about your particles. If you probably need some other measurement to go along with it, maybe a scattering measurement, but it's possible that you can actually take advantage of the fact that the LAI is different. Yes? The effects on. So can the coding change depending on? Yeah. So this is a question. It doesn't seem in our experiments that the coding enhances, even though in some experiments it shows that the coding enhances the absorption. The jury's still out on whether coating enhances. So the theory is that coating has a lensing effect. So even though it's not absorbing, you have a change in the density and the index of refraction at the surface of the particle with the coating, and it can cause a lensing effect. So you can get refraction of the light into the particle itself. So it basically makes your particle look bigger to the laser. So it increases the cross-section. But the jury's still out on whether the results I just showed you indicate that there's no coating effect on the absorption cross-section. But that's something that really needs more investigation.
Yeah. Kind of a follow-up on that, for the lensing then.
Oh.
Kind of an amorphous shape that causes it to
Yes.
out instead.
Yes, so the question is, when you say that coating has an effect, increases the absorption cross-section because of a lensing effect, you're ignoring the fact that the particles actually can shrink when they get coated, when they do restructuring. And yes, that is an effect. And people are also trying to understand that effect. Yes, absolutely. There are a whole number of papers that are coming out on that, yeah. Oh, different flame temperatures. So the question is, do you see these effects at different flame temperatures? And the answer is, so all the experiments that we did with coating is with coating is not in a flame. We did it outside of a flame where we could coat and not, the effects of temperature on the particle in a flame, that will affect your decay. Okay, so this is a really good question when you're implementing just LAI to get a particle size. You have to know the flame temperature in order to get an accurate conductive cooling rate, because you're right, the rate is going to depend on the particle temperature relative to the flame temperature. Usually you're heating the particle up to like 4,000 Kelvin and the flame is like 2,000 Kelvin or 1,500 Kelvin, but still has an effect. You still need to know or have an estimate of what the temperature of the flame is where you're making that measurement. Yeah, so that's a really good question, yeah. Okay, yeah, okay. Okay, so I think you could actually use, so it complicates particle sizing, but I think you can actually use some of this information, especially if you combine it with other measurements to get some more information about your particles. Okay, so here's where we are. We've gone through all these different diagnostics. So the first part was in ex situ composition. We did maturity, size, particle size, and all these different techniques that are available to you currently to get information about your particles. So the next part is about like exactly this question, what's your flame temperature? Sometimes you actually need to understand some of these complementary parameters in order to make your measurement, okay? Or in order to model your flame. Maybe you make the measurement, but you actually need all these other, if you want to model things, you need all these other parameters, right? Okay, so what are the diagnostics we can use to make those measurements? And some of them are really cool and really fancy. This is one that is a good workhorse for measuring temperatures. Thermocouples, we've been doing this for ages, right? Thermocouples. And we still use thermocouples. You just have to be careful when you have a sooting environment, because the soot will cover your thermocouple, and the thermocouple measurement depends on the emissivity, and a coated thermocouple has a different emissivity. So you have this range of thermocouples. People have tried different types of, like bead sizes and composition and stuff, and still there are papers coming out. This one's in 2023, right? It just recently came out on thermocouple technique for making measurements in sooting flames. Okay, so when you're making this type of measurement, usually what you do is you stick your thermocouple in, And you measure, basically, the temperature tells you as a function, the signal, the voltage as a function of time, right? And then you usually extrapolate that curve back to 0 time, because what's happening is you stick the thermocouple in and it starts to heat up, but meanwhile it's getting coated with soot. So you really want to know what was the temperature without the soot on it, what would it have measured? So this is what people normally do, is they extrapolate back to 0 time to get the temperature from the thermocouple. Okay, pretty straightforward. Stick that in there. The part that's not like straightforward is like just making that measurement as a function of time, right? So then this group like compared to other diagnostics, right? So here's the temperature as a function of height above the burner with different like NO. We'll talk about this in a bit. NO and OH, laser-induced fluorescence. They use different correction techniques to try to back out the actual flame temperature at different locations, and then they calculate the flame temperature, and it does a pretty good job. Unfortunately, when you're trying to understand chemistry, you're hypersensitive to temperature, so you really want to get the best measurement of temperature you can if you're really trying to simulate the chemistry that's going on in the flame. Okay. Optical pyrometry, another workhorse that we've been using for a long time. Again, this is the same group I was showing you before doing optical pyrometry. You have the Planck function, right? You generally make an approximation that this exponential function is much greater than 1, so that denominator in the Planck function you don't have to worry so much about if you because you want to take a ratio at 2 different wavelengths, and it's a lot easier if you can get rid of that -1 in the denominator. And you end up with an analysis that looks like this, a temperature, as a function of 2 different wavelengths, signal at 2 different wavelengths. But you need to understand the emissivity is what we already talked about just a little bit, with you need to understand the emissivity of the particles. So if you have a way of measuring the emissivity, getting the dispersion exponent, you can make this measurement. Here's what this group did. And then what I want to show you this because remember I just was showing you that they made all these measurements where they got the dispersion exponent as a function of position in the flame. I was just showing you that in the last, a few graphs ago. So their dispersion exponent they call alpha. So this is the 1, 2, 3. The 4th graph over says T measured alpha. So that's the temperature they derive from the Planck function with their measured dispersion exponent, okay? If they just assume that the dispersion exponent has a value of 1.38, which people have used in the literature, they get the next one over, and then the delta T is the difference between those 2 values for dispersion exponent. So there is an error if you just ignore the fact that the dispersion exponent can change depending on the soot maturity. Okay, so just be aware, and it's a pretty significant change depending on 60. I think that's Kelvin or Celsius, whatever. It's a delta, so it's 60 Kelvin, right? Difference in temperature. It's not huge, but it's there if you're doing theory, just to. And it changes depending on how mature the particle is. And then there are these multispectral techniques. In this case, this is an absorption technique where they look at the spectrum of gas phase species. This is IR. I think this is an IR measurement, mid-IR, sending the mid-IR through the flame. So you're getting molecular species, so you're getting internal states, vibrational, rotational states of molecular species in the flame. And that according to the Boltzmann distribution, gives you the temperature of the molecules. So this is the type of measurement they make, and they can see for like the different small species in the flame, they measure their internal state distribution and get a temperature of the gas phase. Okay? Okay, this is really interesting. There have been a number of papers. This is another synchrotron type measurement. So in this measurement, they send X-rays, and I can't remember what, 14.3 keV, so hard X-rays, into a flame that has seeded with krypton. And so krypton will absorb and emit at this photon energy. And what they can do is look at the density of krypton in the flame as a function of height in the flame, and then the density can be mapped into a temperature, right? If you know the pressure, then the density of the krypton, right, gives you temperature, just through the ideal gas law. So this is, let's see, they have the density of on the left-hand side, and that's mapped into a temperature. So that's a measurement where I think they just did absorption of the X-ray in the flame. And then this one, they did fluorescence, so that krypton can absorb and then fluoresce. So they did the same thing, but then they looked at the fluorescence signal and got the density of the krypton to map that into a temperature using the ideal gas law. Yeah, so it's cool that they can do this and get nice temperature distributions. I don't think I've seen a good comparison of this technique with other temperature measurement techniques. And then this is something that is easier to do in the lab. It's a two-line atomic fluorescence. Again, you seed your flame with a good atomic species. In this case, it was, I think we need a break. You're supposed to tell me when there's a break time. Okay, so let's take an extra 5 minutes after the hour, and then we'll come back, finish up this, and start an atmospheric. Okay?